Hey everyone. So just to recap, so far in this unit on circuits, we have talked about some of the basic characteristics of circuits, talking about things like current and resistance and how those describe and affect the functioning of circuits. And then we've also started to talk about slightly more complex circuits that have multiple resistors, multiple devices, all connected together on the same circuit. And so in this lesson, we're going to start trying to bridge the gap between those two different lessons and talk about how we can start analyzing current and resistance in circuits that have multiple resistors and multiple devices in them. So just to recap a couple key ideas here. Before we can even dive into this idea of equivalent resistance, we have to be really solid about our understanding of the different ways that resistors can be connected to each other in a circuit. So as a reminder, there are two major types of circuit connections. One is series. And resistors that are in series with each other are on the same current pathway, which basically means that any current that goes through one resistor has to also go through the other resistor as well. They share the exact same current, and there's no mismatch in their current at all. The other possible type of connection that we can see is parallel connections between resistors. And resistors in parallel are on different pathways, which mean ultimately that current either goes through one resistor or the other one, but never both of them, one after the other, right? So depending on how we're adding our resistors together and whether we're combining multiple resistors in series with each other or in parallel with each other, that's going to have a different impact on the overall obstacles that the current is facing. And so this brings us to this idea of equivalent resistance. And equivalent resistance is basically just a description of what is the overall combined effect of all of our resistors in series or in parallel. Or essentially, if I have a whole bunch of resistors that are all connected to each other, what one resistor could I replace that whole mess of resistors with that would have the same overall effect on the current that is traveling through the circuit and being drawn from the power source? Okay, so equivalent resistance, just like the sum total outcome of our many resistors that are all connected to each other. And whether resistors are connected in series or parallel makes a big difference in terms of what that equivalent resistance is. So let's start with series, the nice, simple kind of way to connect things together. So if we add resistors in series, so if I start off with one resistor, and then I connect another resistor in series with that first one, what's going to happen to the equivalent resistance based on what you saw in the investigation? Now, I'm hoping that you saw that as we add more resistors in series with each other, the equivalent resistance keeps going up, which means basically that as we add more and more resistors in series with each other, there's going to be more and more obstacles to our current. Our current's going to get slowed down more and more because we're essentially creating more hoops that our current has to jump through. It keeps getting slowed down more and more. There are more and more traffic jams along the current pathway. Now, more specifically then, we have a formula to calculate how that equivalent resistance will be affected by each of those individual resistors. And I'm just wondering if you can guess what our formula is to calculate equivalent resistance for resistors in series. Did you say that they all just add together? Because if you did, you are correct. It's really that simple. You just add up the resistance values of all of your resistors in series, and that's their sum total equivalent resistance. Okay, so for a little example problem, we've got 3 resistors in series in this diagram here. One of those resistors has a resistance of 10 ohms, and the other 2 are 20 ohms apiece. What is the equivalent resistance of that circuit? So since these are all in series, all I have to do is just add together those 3 resistance values. So 10 plus 20 plus 20 gives me a grand total equivalent resistance of 50 ohms. So in other words, I could take all 3 of those resistors, pull them out of the circuit, stick in just one 50 ohm resistor, and it would have the same effect on current. We would get the same current being drawn from the battery if we replaced all that with just a 50 ohm resistor. One key thing to note is that the equivalent resistance then of this circuit is greater than the resistance of any one individual resistor here. So 50 is greater than 10 or 20 or 20. Okay, now that all seems like nice and intuitive and straightforward and whatever, but this is only half the story. We also have resistors that can be connected in parallel. So if we take a nice simple circuit and then we add another resistor in parallel to that circuit, not in series, but in parallel, what's going to happen to the equivalent resistance? Now, this may seem counterintuitive, all right, but ultimately, if we add more resistors in parallel, we're actually going to decrease the overall equivalent resistance. And that feels weird that we can add more resistors and get less resistance than what we started with. But the reason for that is that as we add resistors in parallel, what we're really doing is opening up more pathways for current to get around the circuit from the high to low potential side of our power source. So it's kind of like opening up additional lanes on the freeway or opening up additional checkout lanes at the grocery store. Even if there is some sort of obstacle being placed there, even if there is a little bit of like a traffic jam or you have a slow cashier or whatever, the more lanes that are open, the faster we can get everyone out, the less of an overall obstacle there is to processing people and getting traffic moving through. And so that's kind of how we can make sense of this idea that adding resistors in parallel actually decreases the overall equivalent resistance. Now we have a formula for this as well. My guess is that this one's a little bit harder to intuit even after collecting some data. It looks simple, but it's a little bit more tricky to actually carry out. So we still have this idea of summing up all of our resistance values, but instead of just adding them all up and that's equal to our equivalent resistance, it's actually that the reciprocal of the equivalent resistance is equal to the sum of the reciprocals of all of our individual resistors. So if I take 1 over my first resistor plus 1 over my second resistor plus 1 over my third resistor plus for all of the resistors in parallel, and then I do 1 over that value, so I have to like invert it twice, then I finally get the equivalent resistance. Let's try out a quick example of that. So here I've got 3 resistors that are all connected in parallel, the same 10 ohm, 20 ohm, and 20 ohm resistor that we had in the previous practice problem. So if I want to calculate the equivalent resistance of this circuit, now I have to use my parallel equivalent resistance formula, which says that 1 over the overall equivalent resistance of this circuit is going to be equal to 1 over 10 ohms plus 1 over 20 ohms plus 1 over 20 ohms. So for each of my different resistors. So if I add up 1 over 10 plus 1 over 20 plus 1 over 20, ultimately I'll get a value of 0.2. But that's not the end of the story. That doesn't mean that my equivalent resistance is 0.2. It means that 1 over my equivalent resistance is 0.2. So to get the equivalent resistance by itself, what I have to do is flip that final value and do 1 over 0.2, or in other words, 0.2 raised to the -1 power. You can think of it either way. Those are the same thing, okay? So 1 over 0.2, that's 5, all right? So that means the equivalent resistance of this whole parallel circuit is 5 ohms. All right, so I could take all 3 of those parallel branches, pull them out, and replace them with a single 5 ohm resistor, and it would draw the same current from the battery as this whole mess of a circuit does, okay? Please note then that the equivalent resistance of this circuit is less than the resistance of any individual resistor in there right now, okay? So once again, seeing that as we add resistors in parallel, we're decreasing that equivalent resistance. Okay. So we've got those 2 different equations. That looks cute. Everything's nice and fine and simple if we stick with nice, gentle, only series or only parallel connections. But sometimes we get ugly circuits like this one. Oh, it's so ugly. It's got parallels and series and all these different things. It looks weird, but you know what? you can still analyze this one as well. It may have multiple series and multiple parallels in there, but ultimately we can still break it down the exact same way, right? So here is my step-by-step guide for analyzing and determining the equivalent resistance of a big mess of a circuit like this one, okay? First thing, always draw your current pathways. Get in the mind of the current going through this circuit, if it had a mind, all right? Figure out what are all the ways that current can flow through here. Once you do that, you'll be able to identify your parallel sections. You'll see the junctions where current is splitting, and then the junctions where that current comes back together and reunites again, right? Once you've done that, zero in on one parallel section at a time and look at the different branches that current can take between those two junctions where the current splits and then comes back together, and make sure that each of those branches only has one resistor on it. If any of those branches has multiple resistors in series, go ahead and add those in series first, because that's easy. You just add those two resistances together and voila, you can replace it with just a single resistor. Okay, so knock those things out until eventually your parallel section, all the branches on it have only one resistor on them apiece. Once you've done that, then you can take the equivalent resistance of that whole parallel section using our 1 over Req equals 1 over R1 plus 1 over R2, blah, 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 from there. Okay, so you condense that whole parallel section down and find its equivalent resistance. And then if you have anything left over in series, you can go ahead and add that in at the end. I realize that this doesn't make a lot of intuitive sense right now. We will work through some practice problems with this later. But this is just the general approach that we're going to be taking. All right. Now, to make sure that we are clear on these ideas, a couple quick check for understanding questions. So as it turns out, you've got a circuit breaker at your house that is connected to all the circuits in your house. And if any one circuit draws a current greater than 12 amps, that circuit breaker will trip and all the power will get shut off for that circuit. So if you were worried that one of your circuits in your house was drawing too much current, but you really needed to attach some more devices to that circuit, would you want to add them in series or in parallel? You're going to want to go ahead and add those in series at that point, because if we add these resistors in series, we're going to increase the equivalent resistance, which is going to decrease the current. Whereas if we added them in parallel, we're opening up more current pathways and we're actually going to draw more current from our power source. Right? Second question for you to consider. It used to be old Christmas light strands would have all the bulbs connected in series, but nowadays if you buy Christmas light strands, what you'll have is a number of parallel connections in those, which is why we end up seeing like multiple wires connecting our lights together. Why would this change be made? Why would consumers want their lights connected in parallel rather than in series? Well, there could be a few different reasons, but two of the main ones include that number one, the bulbs are brighter because we're able to draw more current, and then as a result, then we're getting lots of current flowing through and each light bulb getting adequate power that way. So we see that our bulbs are going to be brighter in parallel than they would be in series. So that's pretty if you want your light bulbs to be lighting up. The other thing is it's a common like comic trope that with the old Christmas light strands, if one bulb burned out, none of them worked, because again, if we break any connection in series, the whole circuit is open and we don't get current to flow through any of our devices. But in parallel, all of our lights would be on different pathways, and so you can lose a light bulb and not lose the entire strand. All right. Things to think about with that. We will continue diving more into calculating equivalent resistance and analyzing complex circuits in the coming days. Thanks for watching.